So, we are discussing about the vibration of a molecule, and we have seen that this vibration of a molecule, it's a similar problem of simple harmonic motion or simple harmonic oscillator. Okay. And we have seen this solution of simple harmonic oscillator is known to us because it is a standard problem in quantum mechanics. So, what we have seen this basically simple harmonic vibration of a molecule. This if we take model, this basically model, if we take model that it's a model of simple harmonic motion, simple harmonic oscillator. So, you can see this when we tell this simple harmonic motion. So, this its potential energy basically it changes like this. Okay. So, this is the energy, and this is the distance between two molecules, two atoms of the molecule. So, R0 is the equilibrium distance or bond length. So, its potential energy is half k r minus R0 square, or if you take this change distance from this equilibrium position. So, then r minus R0 one can take it is x. Okay. So, the just displacement from the equilibrium position, if you take as x. So, x is nothing but r minus R0. So, half k x square. Okay. So, then this potential is symmetric basically, and this kind of potential of any particle, it's nothing but the simple harmonic motion, simple harmonic oscillation. So, so in this case, so when it is oscillating, it has natural frequency, that frequency omega 0 equal to square root of k by m. K is this bond strength basically, and mu is the reduced mass. And so, corresponding nu 0 frequency, this is the angular frequency, yes. So, corresponding frequency nu 0 1 by 2 pi omega 0. So, square root of k by mu, and then in wave number, so just you have to, so nu 0 equal to c by lambda. So, 1 by lambda is nu bar. So, nu bar will be, so divided by c. Okay. So, 1 by 2 pi c square root of k by m, that will be in centimeter inverse in wave number. Okay. So, here I have used this in place of omega, in place of this nu bar, I have used this omega 0 bar. So, just generally nu bar we use for to represent the spectral, that wave number of spectral lines. So, that is why just to differentiate it. So, this omega 0 bar I have written, but it is nothing but the nu bar. Okay. So, as I mentioned this in quantum mechanics, simple harmonic motion is a standard problem, and its solution gives energy, that is E v equal to v plus half h cross omega 0. Okay. And v is the vibrational quantum number, v can take value 0, 1, 2, 3. Okay. So, in wave number energy levels, energy in wave number, so nu bar, this nu v. Okay. So, in different notation I have written that equal to that's Hc E v by Hc. Okay. So, that v plus half omega 0 bar. Okay. So, this is in joule, energy is joule or electron volt, whatever. Okay. And here this energy is in centimeter inverse wave number. Okay. So, if this is the energy expression, so in wave number if I plot. So, this will be the energy levels for V equal to 0, 1, 2, 3. So, just one can draw lines from the energy for different value of V. So, this will be the, and you can see this V equal to 0. So, it is a half omega naught bar, then V equal to 1 3 by 2 omega naught bar, 5 by 2 omega naught bar, 7 by 2 omega naught bar. So, these are increasing with so separation between these energy levels are basically same for all cases, and that is nothing but omega 0, okay, omega 0 bar. So, here the spectral lines you will get only one, because these all are same energy, okay, if selection rule is del V equal to plus minus 1, and in this case it is seen the selection rule is del V equal to plus minus 1, as the similar case we have seen for rotational spectra, where selection rule was thus del J equal to plus minus 1. So, in this case also this selection rule is del V equal to plus minus 1. So, only single spectral line you will get from the vibration of the molecule under the simple harmonic oscillator model. Means if we consider that the vibration of molecule is nothing but the it is like a simple harmonic oscillator, then this from the spectra means microwave spectroscopy, from microwave spectroscopy, sorry, from infrared spectroscopy or vibrational spectroscopy, we can see this spectra, and we should see, or we will see only one spectra which will have the frequency omega 0 bar in centimeter inverse, okay, means in wave number. So, that is the case for a vibration of molecule when we are considering the simple harmonic motion, okay. So, but it is seen that this it is not the case, you know, it is not the only one spectral lines we are seeing in case of vibrational spectra of a molecule, but only one line is very strong, and there are some other lines, although they are comparatively very weak, but other lines are also there. And what are the source of those lines? So, then it is realized that this, considering the simple harmonic motion, simple harmonic oscillation model. So, it is an ideal case, okay. So, real molecule actually deviates from this model, simple harmonic oscillation model, and its vibration is deviated or distorted from this simple harmonic oscillation, okay. So, that is basically called anharmonicity or anharmonic oscillator, okay. So, simple harmonic, so one model was basically simple harmonic oscillation, okay. So, simple harmonic oscillation, what does it mean? So, in case of say if we have reduced this this problem to one body problem. So, that is it's like a spring, okay. So, it's oscillating. So, this the this the this distance, this the say r0 position, equilibrium distance. Now it is oscillating. So it is simple harmonic oscillation when we will consider that its displacement in this side and its displacement from here, this other side, it is symmetric. Other side it is symmetric. Okay. Okay. So from here it is going, so it is oscillating like this. It is oscillating like this. So this expansion and compression, these are symmetric. Okay. The amount is expanded, okay, that it is compressed with the same amount. Okay. If so, then we tell it is simple harmonic oscillator. But in reality, in case of molecule, this model is really not suitable. It is slightly deviated from this model, and that is called basically anharmonic oscillator, harmonic oscillator, simple harmonic oscillator. If I write oscillator, okay, then another case is anharmonic oscillator. So what is that? It is when this oscillation in both sides from the equilibrium position, if it is not symmetric, if it is asymmetric, means the amount it expanded, okay, for same energy, its compression is not same. Okay. For same energy, its compression is not same, or other way, for same expansion, whatever the energy of the system, for same compression, same amount of compression, the energy of the system is not same, it is different. And it is seen that due to the compression, same amount of compression, its energy is higher than the same amount of expansion. Okay. So, from where this asymmetry comes? So, that is basically because of real molecules. So, in real molecules, what we have seen, you have a nucleus and this electronic charge surrounding it, and another molecule, another atom. So, it has electronic charge, okay, and I have shown you this, its energy changes when you are changing the distance between these two. So its energy changes. Its energy changes as I showed that its energy changes like this. Okay. So what does it mean? Its meaning is that when, that means this is the equilibrium distance. Now when it is expanded, say by this amount, so its energy changes. So energy changes from here to here. Okay. When it expanded, fine. Now if it is compressed, if it is compressed by same amount, okay, if it is compressed by same amount, so like this, so its energy will be like this, energy is like this. Okay. So, now its energy is higher for same compression and same expansion. For compression this energy is higher. Okay. So, if you so energy change is not symmetric due to compression and due to the expansion. Reason is that this side as I told, that change of energy is very, rate of change of energy is very high. Its sharp change when slight distance, when slightly it is compressed, but when it is expanded, okay, this molecule bond length is slightly extended, okay, its change of energy is like this, its rate of change of energy is very slow. Okay. So, that is why the change of energy due to compression and expansion is not symmetric. So, that is why in real molecule this we see the change of so in this case whatever we have considered that this change of energy is symmetric, but in real molecule the change is basically its sharp, change is sharp, and here change is slow, and then it goes to the, it is just like this, it goes to the saturation value. Okay. So, this is the potential, this is the energy, this for this energy when it is harmonic oscillator, when molecule will behave like harmonic oscillator. So, this will be the change of energy due to compression and expansion, and this will be the change of energy, this curve will be followed when this oscillation is anharmonic. Okay. And in reality, in real atoms, so it is not harmonic oscillator, it deviates from this harmonic behavior, and some asymmetry introduced in this behavior, and thus it is called basically anharmonic oscillator. So, for anharmonic oscillator, so our potential energy curve is basically will change like this. Okay. So, this is the equilibrium distance r 0, and here it is 0, here it is change of r, okay, and this side is change of energy. Okay. So, this anharmonicity basically so for this harmonic oscillator, the potential energy, we have seen the potential energy is half k r minus r 0 square. Okay. So, that is why it is symmetric. So, that is the potential energy. Now, for this anharmonic oscillator, so what is the potential energy? Okay. What is the potential energy? So, that just purely empirical formula was given by P.M. Morse. One empirical formula was given by P.M. Morse. Okay. Fitting the experimental curve, this P.M. Morse, he deduced a empirical formula and he gave this potential energy for this anharmonic oscillator or which follows this curve. So, this E is equal to basically d E, it is d E 1 minus e to the power minus beta r minus r 0 then square, okay, then square. So, this kind of potential energy, this is a purely empirical formula, but it fits this experimental observation, okay, and this potential energy curve, it is a this follows this function and it is called Morse function. Morse function, it is called Morse function, okay. So, one has to use this potential energy in place of this this potential energy, which is for harmonic oscillator and this is for anharmonic oscillator. So, using this potential energy, one has to again repeat this calculation. Schrodinger, one has to solve this Schrodinger equation considering this potential energy, and one can find out the energy expression. So, I will write just that energy expression. So, here unknown is d E and beta. So, beta is basically a constant for a particular molecule. Beta is a constant for a particular molecule. So, here I can write beta is a constant for a particular molecule, okay. So, for different molecule beta will be different, it is just constant, and d is called basically this value is basically d E, this value is basically d E. It is called dissociation energy. D is called dissociation energy. This D is called dissociation energy. Dissociation energy. Okay. It is called dissociation energy. Means the molecule will breaks at this energy. So, this energy value is basically this energy, this is the value of this energy. When energy of this energy d energy will be supplied to the molecule, okay. So, this molecule will go in this state and then it is basically that is why it is the constant saturated energy, okay. At that energy this molecule will breaks. So, molecule basically it is vibrating, it is asymmetric vibration, okay. It is basically asymmetric vibration, okay, or the compressed, but it is elongated more, okay. So, energy is higher and higher, so it will be elongated more and more. So, after some time what will happen? They will be separated. So, that is called dissociation. So, to dissociate the molecules, to separate the atoms, how much energy is required? So, that is basically dissociation energy. So, that is d. Okay. So, now considering this Morse potential, one has to solve the Schrodinger equation, and that solution is also will be, one can write E, it is V, E V equal to or at a time I can write I think this with the So, in terms of wave number EV. So, that so what is happening, you see this at lower energy, it is up to this you can see symmetric. Okay. So, when it is vibrating, oscillating with smaller energy, so it's like a simple harmonic oscillator. Okay. But when it is going to the higher energy, so then it is becoming asymmetric, Okay. So, this this solution itself will tell us that this whatever the energy for simple harmonic oscillator, so that was V plus half omega 0, I wrote omega 0 bar. Okay. Here I am writing omega E bar for just for anharmonic case. It is here also D E, I am using this symbol in case of anharmonic oscillator. Okay. So, here I have used D E. So, here I am writing omega E. So, this natural frequency omega 0 and corresponding wave number omega 0 bar. So, for harmonic oscillator, so in this case this wave number omega E bar is not same as the omega 0 bar. Okay, it is different. So, different symbol I have used. So, this V plus half omega E bar. Now, this correction term will come this due to this anharmonicity. So, that is basically minus another term will come. So, that is Xc. What is Xc? I will tell you. Xc V plus half square, okay, omega E bar, Okay. So, here Xe is called this anharmonicity constant, anharmonicity constant. It is called anharmonicity constant. Okay. And it's I think it's related with the omega E and dissociation energy. So, this equal to omega E bar by 4D. Okay. 4D. Okay. So, this is the anharmonicity constant. So, it is related with the dissociation energy, and so this I can write that basically if EV for anharmonic oscillators. So, I can write omega E bar V plus half. Okay. So, then 1 minus Xe V plus half. Okay. So, this I will just remove it. Okay. So, this will be the energy for anharmonic oscillator in wave number in centimeter inverse, of course. So, this just to show that it is in terms of wave number. And for harmonic oscillator, what we saw that energy expression was omega 0 bar V plus half. Okay. So, now if you compare these two, you can write this omega 0 bar Okay. This natural frequency of this harmonic oscillator omega 0 bar, okay, that equal to, so omega e bar 1 minus xc v plus half. Okay. So one can tell that this anharmonic oscillator, it is basically, it's what does it mean? What does it mean of this expression? It is meaning of this is that this anharmonic oscillator, as if it will oscillate harmonically, it will oscillate like harmonic oscillator with different frequency, with this frequency, and that frequency is not same for all energy level, all V, okay, for different vibrational level, for different energy states. This frequency will not be same. This frequency will change with V, and it will decrease. This frequency will decrease with higher energy level, with higher V. Okay. So that's the meaning. So anharmonic oscillator also it is one can consider that it will oscillate like a harmonic oscillator, but its frequency, it is not omega 0 bar. Okay. In that case, omega 0 bar will be this, which will vary with V, for higher V, for higher vibration energy level. So this frequency will be lower, okay, and it will change with V. Okay. So yes, yeah. So in next class I will discuss about the spectral lines of this anharmonic oscillator. So let me stop here. Thank you.